I'm gonna bring you guys with me. So my toes are getting a little bit cold, so I'm just gonna put on my socks here. Ah! And then I brought these little sandals, so we're just gonna put those on just to be like a little bit more warm. And I've also got that I've got like a little thermal over there that I might end up using in a second if I get too cold, but I think I'm fine for right now. I think I'm fine for right now. Alright, so we're gonna keep going. Okay. So we're still in part one, and I think we're still talking about scalability, but now we're talking about describing performance. So once you have described the load on your system, you can investigate. I think this shut off again. Maybe the battery is trying to like conserve itself. I think that's probably what's happening. I don't know. It just keeps cutting off. All right, so let's go back. Yeah, so we're still in chapter 1, describing performance. Actually, if we scroll down, yeah, this one says scalability. So once you have described the load on your system, you can investigate what happens when the load increases. You can look at it in two ways: when you increase the load parameter and keep the system resources like CPU, memory, network bandwidth, etc. unchanged, how is the performance of your system affected? When you increase a load parameter, how much do you need to increase the resources if you want to keep the performance unchanged? Both questions require performance numbers, so let's look briefly at describing the performance of a system. In a batch processing system such as Hadoop, we usually care about throughput, the number of records we can process per second, or the total time it takes to run a job on a dataset of a certain size. In online systems, what's usually more important is the service's response time. That is, the time between a client sending a request and receiving a response. Latency and response time. Latency and response time are often used synonymously, but they aren't the same. The response time is what the client sees. Besides the actual time to process the request, the service time, it includes network delays and queuing delays. Latency is the duration that a request is waiting to be handled, during which it is latent or awaiting service. Even if you only make the same request over and over again, you'll get a slightly different response on every try. In practice, in a system handling a variety of requests, the response time can vary a lot. We therefore need to think of a response time not as a single number, but as a distribution of values that you can measure. In figure 1 through 4, each gray bar represents a request to a service, and its height shows how long that request took. Most requests are reasonably fast, but there are occasional outliers that take much longer. Perhaps the slow requests are intrinsically more expensive because they process more data. But even in a scenario where you'd think all requests should take the same time, you get variation. Random additional latency could be introduced by a context switch to a background process. The loss of a network packet and TCP transmission, a garbage collection pause, a page fault forcing a read from disk, mechanical vibrations on the server rack, or many other causes. So figure 1 through 4, illustrating mean and percentiles response time for a sample of 100 requests to a service. It is common to see the average response time of a service reported. Strictly speaking, the term average doesn't refer to any particular formula, but in practice it is usually understood as the arithmetic mean. Given n values, add up all the values and divide by n. However, the mean is not a very good metric if you want to know your typical response time, because it doesn't tell you how many users actually experienced that delay. That's a good point. Usually, it is better to use percentiles. If you take your list of response times and sort it from fastest to slowest, then the median is the halfway point. For example, let's go back. If your median response time is 200 milliseconds, that means half your requests return in less than 200 milliseconds, and half your requests take longer than that. This makes the median a good metric if you want to know how long users typically have to wait. Half of user requests are served in less than the median response time, and the other half take longer than the median. The median is also known as the 50th percentile and sometimes abbreviated as P50. Note that the median refers to a single request. If the user makes several requests over the course of a session, or because several resources are included in a single page, the probability that at least one of them is slower than the median is much greater than 50%. In order to figure out how bad your outliers are, you can look at higher percentiles. The 95th, the 99th, the 99.9th percentiles are common, abbreviated P95, P99, and P999. They are the response time thresholds at which 95%, 99%, or 99.9% of requests are faster than that particular threshold. For example, if the 95th percent response time is 1.5 seconds, that means 95 out of 100 requests take less than 1.5 seconds, and 5 out of 100 requests take 1.5 seconds or more. This is illustrated in figure 1.4. High percentiles of response times, also known as tail latencies, are important because they directly affect users' experience of the service. For example, Amazon describes response time requirements for internal services in terms of the 99.9th percentile, even though it only affects 1 in 1,000 requests. This is because the customers with the slowest requests are often those who have the most data on their accounts because they have made many purchases. That is, they're the most valuable customers. It's important to keep those customers happy by ensuring the website is fast for them. I don't know what I did. Amazon has also observed that a 100 millisecond increase in response time reduces sales by 1%, 20, and others report that a 1 second slowdown reduces a customer satisfaction metric by 16%. On the other hand, optimizing the 99.99%, the slowest 1 in 10,000 requests, was deemed too expensive and to not yield enough benefit for Amazon's purposes. Reducing response time at a very high percentile is difficult because they are easily affected by random events outside of your control, and the benefits are diminishing. For example, percentiles are often used in service level objectives and service level agreements, contracts that define the expected performance and availability of a service. An SLA may state that the service is considered to be up if it has a median response time of less than 200 milliseconds and a 99th percentile under 1 second if the response time is longer. It might as well be down, and the service may be required to be up at least 99.9% of the time. These metrics are expectations for clients of the service and allow customers to demand a refund if the SLA is not met. Queuing delays often account for a large part of the response time at high percentiles, as a server can only process a small number of things in parallel, limited, for example, by its number of CPU cores. It only takes a small number of slow requests to hold up the processing of subsequent requests. An effect sometimes known as head-of-line blocking. Even if those subsequent requests are fast to process on the server, the client will see a slow overall response time due to the time waiting for the prior request to complete. Due to this effect, it is important to measure response times on the client side. When generating load artificially in order to test the scalability of a system, the load generating client needs to keep sending requests independently of the response time. If the client waits for the previous request to complete before sending the next one, that behavior has the effect of partially keeping the queues shorter in the test than they would be in reality, which skews the measurements. Percentiles in practice. I'm just kidding. Well, I'm not, but alright, let's keep going. High percentiles become especially important in back-end services that are called multiple times as part of serving a single end user request. Even if you make the calls in parallel, the end user request still needs to wait for the slowest of the parallel calls to complete. It takes just one slow call to make the entire end user request slow, as illustrated in figure 1.5. Even if only a small percentage of back-end calls are slow, the chance of getting a slow call increases if an end user request requires multiple back-end calls, and so a higher proportion of end user requests end up being slow, an effect known as tail latency amplification. This is in a reference number 24. Okay, I think this shut off again. Okay, now it's red. So if you want to add response time percentiles to the monitoring dashboards for your services, you need to efficiently calculate them on an ongoing basis. For example, you may want to keep a rolling window of response times of requests in the last 10 minutes. I guess everyone decided to walk their dog at the exact same time. That's very strange. Okay, every minute you calculate the median and various percentiles over the values in a window and plot those metrics on a graph. The naive implementation is to keep a list of response times for all requests within the time window and to sort that list every minute. If that is too inefficient for you, there are algorithms that can calculate a good approximation of percentiles at minimal CPU and memory cost, such as forward decay, T-digest, or HDR histogram. But beware that averaging percentiles to reduce the time resolution or combine data from several machines is mathematically meaningless. The right way of aggregating response time data is to add the histograms. Oh shit, I think I just oh no, what did I just do? Oh man. I think I just skipped 5 chapters. Shit. I'm on page 434. No! I don't know how we're gonna find our way back because I'm not redoing this. Okay, wait. No, we're gonna find it. I am hella far from... Oh, shit. I don't know what I did. I'm sorry, guys. Wait, let me go back. I don't know... Oh, I think I touched the... Oh, I know what I did. Yes, I touched this thing. And yep, I totally did this. Shit. Oh, yeah, okay. So here we are. We're on page 38. We're good. Okay. So, that was it. Rock with me.